So hi everyone, it's our pleasure to have Caio Lauand today for the R theory seminars. Caio is a PhD student at the University of Florida with Sean, and today he's gonna talk about stochastic approximations, and we are very much looking forward to your talk, Caio. So, stage is yours.
Thank you. Yeah, first I'd like to thank the RL seminar organizers for the invitation. I've watched several of these talks and I always enjoyed it, so I'm happy to contribute to one of them. And again, this is joint work with my PhD advisor, Sean Mine. And well, I guess I'll start. So, oh, wait, it didn't go? Okay. So for today's talk, first I'll present the main problem of interest here, which is root finding under the presence of noisy observations. And then I'll talk a little bit about stochastic approximation, which is a methodology to address that problem, and its possible possible problems that might arise if the noise itself has some memory to it. So to begin, I mean, a lot of the machine learning and optimization problems, right, that are of interest to these communities, hinge upon the task of root finding under the presence of noisy observations. In this stochastic approximation formulation of the objective, the goal is to solve the root finding problem you see here. So you have the function f bar, and you want to estimate theta star, which is the root of this function. It's assumed that we cannot observe f bar, but we can observe noisy versions of it, which is f here. And we define f bar to be the expectation of f with respect to this random vector that corrupts f bar. Right? And we assume that we can observe f for any theta of our choice. Stochastic approximation was then introduced in the 1950s by Robbins and Morrow and consists of the following d-dimensional recursion to estimate the solution to this root finding problem, theta star. Right? So phi n is a sequence of random vectors converging in distribution to the vector phi, often assumed to be Markovian. And alpha n is the step size sequence. So common choices included to be either vanishing in n, on the form you see here, or constant. So you held it constant across the many iterations you perform. Sometimes known as the learning rate in applications, right? And so this talk is all about constant gain algorithms. We'll talk a little bit about vanishing gain to provide a benchmark for comparison with respect to constant gain algorithms, but the main focus here is constant gain. So before we talk about stochastic approximation itself, I mean, this is stochastic approximation, but just a few examples to motivate, right? Why would you care about root finding? So consider Monte Carlo estimation. You want to estimate the mean of a function of some random vector, okay? If you have observations of this random vector, either IID or from a Markov chain stationary distribution in its steady state, the natural thing to do would be to calculate the simple path average. And you would estimate the mean of this function recursively as the observations grow, right? You can frame this simple estimator, the Monte Carlo estimate, as a stochastic approximation recursion. So if you multiply both sides by n, this becomes just a sum, and you can express theta n plus 1 as a difference between the scaled version of theta n and the next observation you see. And by adding, subtracting theta n again, and dividing both sides by n plus 1, you finally reach a stochastic approximation recursion. Okay, so the interpretation here is that to perform Monte Carlo estimation, you're trying to solve the root finding problem, which is outlined here in blue, which is what you see inside the brackets. That's the definition of your f bar, right? So that's the interpretation of Monte Carlo in view of stochastic approximation. Another example would be gradient descent. So suppose you have noisy observations of some loss function, and there's a way to compute the gradient with respect to theta, right? You can compute it numerically. You can perform gradient descent in the sequence of noisy gradients, which is, again, by the form of the problem here, they're designed to approximate the gradient evaluated at theta n in this case. There should be an n here. Sorry, It's a typo. It should be an N here. And perform gradient descent, you would essentially solve the root finding problem, which would be finding a stationary point of this gradient, right, in the average sense. Other examples include gradient-free optimization, right, zero-order methods, Q-learning, TD learning, linear regression. And we'll return to this for TD learning soon, right, so just some motivation. So what do we have in terms of theory for stochastic approximation? Well, any of the standard references that you see here in the bottom, you have these results. For vanishing gain algorithms, you have convergence almost surely for each initial condition of the recursion. And the mean square error typically vanishes as of the order of the step size, right? So it's typically slow. And you see here, because of the choice of step size, the optimal rate of convergence would be 1/n, right? If you choose rho equals 1. But that's a bad choice because it causes some problems to the algorithm in terms of dynamics. And one way to accelerate rates while not compromising when choosing the step size, right, is to apply Pouliot-Rupert averaging. So essentially, this is just an average of the sequence of estimates, a partial averaging, right, where N0 is chosen so that you don't have a lot of effect of transients, right? You can choose N0 to be 1 or 0, depending on how you define the first iteration, but it's argued that if you choose N0 to be a little larger than that, you can kill off some of the transient behavior that you don't need. And it turns out that under very general conditions, PR averaging leads to acceleration of algorithms. So for any row that's about 1/2 and strictly less than 1, you have optimal rates. And you also have optimal asymptotic covariance in the central limit theorem. So the central limit theory holds for stochastic approximation, and if you apply averaging, the asymptotic covariance you get is optimal in the matricial sense. So it's something like Cramer-Rawls bound, in which for any other algorithm that converges, you take the difference between its asymptotic covariance and the asymptotic covariance that you get from PR averaging, and the difference is always positive semi-definite. Okay, so that's how we define optimality here. In the case of constant gain algorithms, there's no hope for convergence. Okay, we can only hope for bounds on the neighborhood of the solution. So again, analogously to what you saw in the vanishing gain case, for the constant gain case, the mean square error is dictated by the step size. Under very restrictive conditions, and namely the vector field f being linear in theta, or affine in theta, and the random vector, the random sequence phi n is IID, then PR averaging has been shown to improve performance of stochastic approximation. So for constant gains. So in these restrictive conditions, you're able to see asymptotic unbiasedness of the estimates if you average, and also you converge at the optimal rate of 1/n. However, and specifically, the noise assumption here is very hard to justify in applications to RL, right? F being linear is okay. I mean, TD learning is a linear recursion, but the noise is not IID, and we'll see the problems that arise from such strong assumptions. And so these conclusions are not true in general. So now just again some motivation of the problems that memory and multiplicative noise might cause to the recursion itself. Consider the MM1Q problem. So this is just a reflected random walk, right? So you go up with probability 1 minus mu, and you come down. Of course, it's reflected, so you'll always be positive, but you come down with probability mu. So rho here is just a load parameter. So it just says that you have a negative drift in the Markov chain here. This is a Markov chain. And if this is strictly less than 1, then the Markov chain is reversible, geometrically ergodic, and it converges to an invariant. Its invariant measure is geometric. The law of large numbers and the central limit also hold for this example. So considering this simple scalar recursion, where eta is just the steady state average of Q, right, the Markov chain Q, and W is just some Gaussian IID random variable, and we're assuming that they are independent of each other. Okay, they're mutually independent. So if you consider this recursion, if the load parameter is less than 1, then you have almost sure convergence from each initial condition. However, for if the load parameter is bigger than 1/2, the second moment is bound. The second moment of the error is bound. It goes to infinity. Sorry, it's not bounded. And the problem here is multiplicative noise. So because you have Q multiplying theta there, that creates a huge problem in establishing these bounds.
So Kai, just quickly,
Yeah.
what is the root parameter? Maybe I just missed that.
Oh, sorry. Yeah, so rho is just the ratio between the probability of going up and down.
Maybe you can also say what is theta star here? What is the root finding problem that's being solved here?
Yeah, so this is just for intuition, right? Theta star, because I'm subtracting the mean of Q. So W is your mean, and I'm subtracting the mean inside this whatever multiplies theta, right? Can you see the cursor? Yeah.
Yeah.
So I'm subtracting the mean. So you can see that if you take f is whatever's inside the brackets, right? So if you take expectation of f, you'll get that because this is your mean, since I'm subtracting the mean, and this is your mean, you get that f bar, right? Our function of interest is minus theta for each theta. So the root would be 0, right?
I see.
So this is just an example for illustration. Maybe if I hadn't subtracted eta here, you're estimating the mean of Q, but it's
Gotcha.
just with some additive noise.
And
Okay.
And mu comes where? Okay, this is the
And
probability.
mu is just the probability of going down, and 1 minus mu is just probability of going up in the random walk.
I see. Okay.
Okay. So can I go?
For me, it's good.
So so this is just a linear system, and the main problem that makes everything blows up in the case for the second moment, for example, is the fact that you have noise in the transition matrix for the system. And when you take expectations, right, Q is random, right, it's a Markov chain. So you end up with expectations of exponentials of sums of random variables, and that's very hard to bound. So that is what causes the second moment on this example to grow to infinity, right? Because it's not bounded in this case. Right? It grows with n. Okay. So another example of problems when you relax the assumptions, the strong assumptions for constant gain algorithms that I've shown before, is if phi is Markovian, then there is a bias induced in the estimation of theta star. So, and we'll talk about this as the talk goes through, but essentially we have an expression for that's actually the main contribution of the paper, is to find an expression for the bias and the asymptotic covariance for the case of constant gain stochastic approximation with Markovian noise. Okay, so we do not have asymptotic unbiasedness as we saw when phi was IID. Right? So again, just another motivating example is to consider the linear system, this linear system with additive Gaussian IID noise. Okay, and just consider some cost function that's quadratic on the state. Okay. The goal of this experiment is to use TD learning to estimate the infinite horizon discounted value function. Okay. Yeah, somebody raised the hand.
Yeah, sorry, what's the cost here, and what are we trying to do?
So we're just trying to estimate
just
the value function, right? So we're going to use TD learning to do that.
And what Oh, you've just got it. My bad.
Oh, no, it's okay. So yeah, so the goal here is to use TD learning to estimate the infinite horizon discounted value function, okay, with this quadratic cost on the state for this linear system. So because the system is linear and the cost is quadratic, it follows that the value the infinite horizon discounted value function has a closed form solution and it's quadratic, right? So this motivates TD learning with linear parameterization with a basis that spans J, right? So you choose it to be 1 and x squared. So it captures J within the basis, right? And then we ran this algorithm, right, the TD0 algorithm, to estimate this value function. And these are the plots you see here. So again, because we have extensive literature supporting the existence of the central limit theorem for stochastic approximation, one would expect the averaged variable to be distributing according to a zero mean Gaussian random variable with covariance equal to the asymptotic covariance that vanishes at rate 1 over n, right? And multiplied by square root of alpha, because we had bounds on the mean square error for constant gain stochastic approximation that were of order alpha, plus its limiting value, right, which would dictate where this Gaussian would be centered at. So if we had asymptotic unbiasedness, then this limiting value, PR infinity, would be 0, right? That's what a heuristic we would have, right, based on that previous literature. So we apply that to this problem, and what we see here is actually a piecewise linear trend when you compare the L2 error, the L2 estimation error, as alpha grows. So according to this heuristic, if the recursion was unbiased, then you would see a linear trend parallel to square root of alpha. But for some alpha that when you increase the number of alpha, and because you're looking at a finite horizon, right? There's some alpha there that is a threshold for when alpha dominates over square root of alpha, right? And that's what you see here. So this indicates the presence of bias, right? And bias of order alpha, as the agreeing to the expression I've shown previously. And then here on the right side is just a comparison of the same problem for multiple initial conditions, independent runs, and a comparison between one choice for vanishing step size and one choice for constant step size. And you see here that histograms for the vanishing, these are the histograms of the estimation error for PR average for in both dimensions of the problem. And in the vanishing gain case, in the vanishing step size case, you see that the histograms are always centered around 0. And their variance is a little bit smaller. It's hard to see, but the variance is a little bit smaller than the constant subsize one. And the constant subsize one, you clearly see that the error is centered around a value that's not 0, so indicating there's bias. I think there's another question.
Yeah, we have one question in the chat from Pawan about the presence of noise. Are the measurements noisy, or the estimates of the states being noisy as well?
Yes. So I mean, we're not estimating states. We have access to the states, and the only noise that's present there is the additive noise you see in the equation that the evolution of the state, right? The equation that defines the system. That's all. That's the only noise there. What happens is it's additive. It's IID, but when you pass it through the TD learning algorithm, because of the second vector here, the eligibility vectors, they're multiplicative in the recursion, and they're the ones that cause memory to carry over. And then I think David had another question, or?
No, sorry, I was just going to point out the question.
Oh, okay, great. So yeah, so what we saw here is independent runs, constant gain algorithms lead to biased estimates, while the vanishing gain don't. Okay. So now let's talk a little bit about theory. right? So again, going back to the original problem, we want to solve a root finding problem. We want to find the root of f bar, which is theta star, and f bar is defined as the expectation of some vector field that depends on theta and phi, a random process. So the design and analysis of stochastic approximation is based upon a deterministic ODE, which is the mean flow. It's the ODE that's determined by the vector field f bar. Okay, so if this ODE is stable, then we achieve our goal, right? So if that would mean that theta star, if it's stable to theta star, then that would mean theta star is the stationary point for this ODE, right? It's like equilibrium for this ODE, and we'll eventually solve the root finding problem for that is of interest to us. The stochastic approximation recursion is then viewed as a noisy Euler approximation of this deterministic ODE. And maybe it's clear once I make a change of variables here. So all I'm doing in the second line is adding and subtracting f bar of theta n to the recursion. And you clearly see that the stochastic approximation can be framed as a noisy Euler approximation of the mean flow, the deterministic ODE, the mean flow ODE, plus some noise that's multiplied by alpha in this case, because it's constant, right? And then showing convergence of stochastic approximation just boils down to showing that Euler approximations are robust to noise. And it is true under very general conditions. One key condition is to assume Lipschitz continuity of the vector field f. Okay, this has been assumed in all the theory for stochastic approximation. Okay, so it's crucial. But up until now, the only representation I have for this noise is it came from a change of variables, right? So can we do any better than that? And the answer is yes. So we can actually apply techniques from Markov processes and to obtain better representations for this noise you see in the Euler approximation. And specific, one key technique, a workhorse that enables this representation is something called Poisson's equation. So Poisson's equation is the second equation you see here. And whenever you see a hat above a function, it just means it's the solution to Poisson's equation for some input or forcing function f. So if f hat solves this equation where the input is f minus its steady state mean, then f hat is the solution to Poisson's equation with forcing function f. Okay, and if we apply Poisson's equation to this noise decomposition delta you see at the top, we obtain a disturbance decomposition that's been introduced in the 80s by Métévier and Priore. Okay, and yes.
Sorry, could you talk us through a little bit more of the Poisson equation? So we're saying that the conditional expectation of the difference of the solution for the two time steps, and we're conditioning of theta n being equal to x. So you're effectively integrating out theta and phi n plus 1, right? But
yeah, so theta is fixed here. I should have said that. So
yeah, so
the
what's
solution,
x? Because x doesn't seem to feature on the right-hand side, and it's not.
It's a typo, Caio.
Yeah, it's a typo. Yeah, it should have been. Yeah, the right-hand side is a function of x too.
Oh, okay.
Sorry.
So the right-hand side should have f theta of x in it.
Yes.
Okay, so
X, that's a lie.
Yeah.
So we want that the difference from the true solution for theta and the solution perturbed by phi of n is the same as the expected solution from phi of n to the next step for some other function f hat. If you find a function f hat such that the difference from now to next step in expectation is the same as the difference of f to the true solution, then that's the solution to the Poisson equation?
Yeah, so f hat is the steady state mean of f, right?
Oh, no. F bar.
F bar. I'm sorry. Yeah. I thought you were talking about F bar.
Oh,
Yeah. Sorry. Yeah. F bar is the steady state mean. F hat is the solution to the equation.
Yep. So could you just give me a tiny bit more intuition for what this is and why this is a useful thing to look at?
Well, it's just a tool for analysis, right? It will be useful when you talk about ergodicity of the Markov chain, for example, because it will empower you to look at if you a condition expectation here would just be a one-step transition of f hat. So when you look at like ergodicity for the Markov chain, it would allow you to get bounds on the open-up functions, for example, a change in the open-up function, for example.
Okay, I guess let's
Maybe
move on.
Dr.
I don't
Manch
think
might have
my background on controls is not strong enough to.
Well, it'll be clear, Caio, when you explain what that delta n, when you point out the terms there, you've got
yeah.
so you're going to put it to use right now.
Right. Yeah. So yeah, if you apply Poisson's equation repeatedly to the terms you see in delta here on the top, you're able to obtain this disturbance decomposition that was introduced in the 80s by Mettevi and Pierre, in which the first term is a Martingale difference sequence. And then the middle terms is just a telescoping sequence. And then the final term is a sequence, is a stochastic process that will be responsible for the bias in the algorithm.
What is TM? Oh, you give it here. Okay.
Oh yeah, so their definitions, they're just functions of the joint process, theta phi, right? And they're defined in terms of Poisson's equation. So you use Poisson's equation to get this representation for the noise, in terms of a Martingale difference sequence, a telescoping sequence, and some sequence that will become important as we'll see next. Okay, so that's where it's used. Okay. And then I guess there's a question here. Is this noise on the measurements assumed to be continuous? No, I mean, the only assumption that I've talked to about now is that phi is a Markov chain, right? It's a geometrically ergodic, aperiodic Markov chain, but it's not assumed to be continuous.
Okay, so maybe I can ask a clarifying question here. This Poisson equation is a clever decomposition of the noise,
right?
That allows you to write this delta n in this way as a difference. You have the martingale, you have the telescoping thing, and then you have the gamma. And like in this trivial case where the phi's IID, then the expectation of the theta and phi n plus 1 would just be f bar. And everything is kind of trivial. And in the Markov case, okay, it's constructed so that you have this property.
Right. Okay.
Good.
Oh, sorry. Okay, so now let's talk a little bit about assumptions. So that's what I was talking about. No, I'll go over it. So we assume phi is an aperiodic Markov chain in a general state space X, and that it satisfies this drift condition. So this drift condition is needed for us to be able to get moment bounds, because again, remember the MM1Q example that I talked about. We need to bound expectations of exponentials of sums of random variables, right? So, and this drift condition is what allows us to do that, okay? To establish convergence, we would only need geometric ergodicity, but but to obtain moment values, we need this hard condition. So this is just a drift condition for the Markov chain. Okay, and that's what I was talking about, seeing the value of Poisson's equation. So you see, you can frame this as a Poisson equation, kind of. Yes.
Sorry, me again. I've not seen something like this before. I guess to me this looks like a conditional moment generating function bound. But then on the right-hand side, what is B times the indicator of S?
Right. So yeah, V is a Lyapunov function. W is some function that will be used in the end. It's some unbounded function, okay? And we'll be using the analysis as a weighing function to define an L infinity space, okay? And S is what's known as a small set. So it's basically a compact set, for example. It depends on the application, but generally is a compact set in Rn. Okay. So are you familiar with Lyapunov's theorem
10 years ago.
in control and stability of
Yeah, I
systems?
did 10 years ago, unfortunately. So just to confirm, what is the subset S, the capital S? What is the subset
Of the state space.
of the state space?
Yeah.
Okay.
But it depends on the application, right?
Okay.
So like for a Markov chain, that's a linear system with Gaussian disturbance. I think every complex set is a small set.
Yeah, and finite sets for countable state spaces. But I see the point of confusion. There's another typo. It should be the indicator function that X is an S. So there's a missing X there. That's confusion.
Right.
Yeah.
Right.
That's the indicator. That's the indicator function. It's 1 if X is an S, or 0 otherwise. So that's why there's a negative drift until you reach this at S, and then you might pop out. Yeah.
Oh, okay. Yeah, fine.
So you have V tends to go
Yeah.
down, and then yeah. Okay. Cool.
Okay. So yeah, just a little bit of discussion on DV3. So DV3, this weird condition appears simultaneously in large deviations theory, and it's known as the Donskans and Varadhan's condition in this literature. And it's also a version of Fleming's nonlinear generator from the optimal control literature. Right. So the second equation here is just Fleming's nonlinear generator, and you can see that DV3 is a special case of that with this choice of H. Right? So, and this implies geometric ergodicity of the Markov chain. Another assumption is Lipschitz continuity, and the form that we choose here is that L is a function instead of being just a constant across all state space, and it depends on X, right? And this is needed because of we're dealing with multiplicative noise. So and W in DV3 is a weighing function for, we will assume that L, the soup, the ratio of L and W, if you take the soup and take the limit as n goes to infinity, it goes to 0. But it's fine. Right. So it's like L grows slower than W. And then we assume global asymptotic stability of the mean flow, which is that deterministic ODE dictated by the vector field F bar, right? Our goal. And asymptotic stability of something called the ODE at infinity, which is a scaled version of the mean flow. So you scale it inside the vector field and outside, and take the limit as the scaling factor goes to infinity. And we assume that this defines a vector field, the limit exists, and that this ODE is asymptotically stable. And that F bar and the Jacobian of F bar are Lipschitz continuous, and the Jacobian of f bar evaluated at theta star is Hurwitz. And now I'm ready to state the main results. So after all that, what are the main results of the paper? So under these assumptions, we're able to prove that each of the terms in the noise decomposition is uniformly bounded, right? Where the bound here depends on the initial condition, but uniformly bounded in L4. And that, again, we have L4 bounds on the estimation error. And they agree with the previous literature's bounds that the mean square error is of order alpha, for example. So this agrees with the previous literature. And this is all for, sorry, I should have said, this is all for general nonlinear stochastic approximation. Okay. And we have a bound on the target bias. So remember, our goal is to find the root of f bar, which is theta star. And here is just a bound on the bias of this target. Okay. And you see them subs here because we don't know if there's a invariant measure at this point, a unique invariant measure at this point. So, and you can kind of see that upsilon, I should have left here, sorry. So again, recall that the disturbance decomposition has a martingale difference sequence, a telescoping sequence, and some vector upsilon that is claimed it was a source for bias. And you can see its effect here. So upsilon dictates target bias for stochastic approximation, for example. It's dictated by this by the expectation of this vector. Okay. When we restrict to linear stochastic approximation, right, meaning that f is affine in theta, and this is just the definitions, right? We have some matrix A that is a function of the Markov chain, so there's some multiplicative noise there and some additive noise as well. And this is the vector field, right? So again, the root finding problem of our choice is just minus A inverse B, right? The root of this equation, this vector field. I mean. So in the case of linear stochastic approximation, we have that the joint process is itself a Markov chain, and it admits a unique invariant measure. And then it makes sense to talk about bias. So with respect to this unique invariant measure, right? So the first result here is that the bias for linear stochastic approximation, and you can kind of see it from the previous target bias bound, because we have a unique invariant measure, this becomes limits, and it's just a matrix inversion, since f bar is just A times theta plus some constant. We have that the bias is of order alpha, where it's alpha times some mean of upsilon, and upsilon star here, recall that each of these functions are functions of the joint process, theta and phi. Whenever I put a star, I just mean I evaluate these functions at theta star, okay? So upsilon star that you see here is just upsilon evaluated at theta star, but with the noise is not held fixed. And we're taking a steady state average with respect to this invariant measure of upsilon, and that defines upsilon bar. And that's the main contributor to bias. Okay. If we apply PR averaging, we cannot get rid of this bias. So that's another result of the paper, and we have an expression for the bias in terms of this solutions to Poisson's equation. Okay. In terms of covariance, we have that the asymptotic covariance for constant gain algorithms deviates from what's optimal, which is sigma star, by some error of order alpha as well. And Z is just a function of asymptotic covariances of the vectors you see in the disturbance decomposition. So whenever you see a sigma CLT, it just means it's the asymptotic covariance of the stochastic processes in the top, right? So it's just asymptotic covariance of this stochastic processes centered. right? Of course, the martingale difference sequence has zero mean, but I just put it here for you to see eccentric. So each of these terms are asymptotic covariances or asymptotic cross covariances of the stochastic processes you see in the noise decomposition that came from Poisson's equation. And Z0 is bounded in alpha. Okay. This we proved that this term is of order alpha. So this error is indeed of order alpha because this is bounded in alpha. It might look scary because you see 1 over alpha here, but this error is of order alpha. Okay. And
Can on this slide,
yes.
Can I ask a question? So alpha here is a step size, and you choose it constant. Is that right?
Yeah. It's alpha constant.
Okay. So how do I need to interpret this? Like, if I set alpha to be 0, then would the bias vanish? But you're not updating the parameter. So
yeah.
What happens if I make alpha very small?
Let me see if I can find. Yeah. So
but you
look at the recursion. There is no point, right?
You're about to show. Your numerics show that beautifully.
Oh, right, yeah. But just to address before I go over vanishing, I mean,
those small alphas in you.
Exactly. If you set it to 0, you're not calculating anything, right? But if you eventually it's 0, then I'm about to show.
Yeah, you're about to show that.
Yeah. So, so consider this linear recursion. Okay, you have multiplicative noise with lots of memory. So W here is just a stochastic process. And at each time step, N is Gaussian and IID. And you're adding these contributions to the previous step of W, right? So W is just like an accumulation of this vector, of this IID Gaussian variables. So this is actually a caricature or a simple version of TD learning. It's something like this in TD learning for the multiplicative noise. And so you have multiplicative noise on the recursion and also additive noise for this process with lots of memory. And if alpha is vanishing, then this is what happens. Just like predicted by previous stochastic approximation literature, right? The estimates are asymptotically unbiased. So even without PR averaging, you see that as n goes to infinity, then the estimates converge to the optimal solution, theta star, right? And PR averaging just accelerates it. So here's our 2 choices of step size, right, for vanishing in it. In the fixed step size case, for this recursion, this is the expression for bias. We can compute it in closed form. This is an approximation, but we can compute it in closed form. It's in the paper. And here's a comparison between multiple independent runs. The run length is not that big, but you can already see the effects of the dichotomy between choosing a constant and vanishing step size. So the first row here is for these independent runs is the empirical mean and variance of the estimation error. Okay, so you see that here's for 5 choices of alpha, and you see that they vary quite a lot. I mean, they grow quite quickly with increasing alpha. There is one good, and the dashed line is just the optimal solution here for the case of me, for the case of the empirical mean. Okay, it's just theta star. There is one good value of alpha that generates approximations that are okay, and that's 0.0028, and it took a lot of tuning to achieve that. But across the board, you can see that the empirical mean of the estimation error varies quite a bit, right? And the same is for the variance. 0.0028 generates a good value. 0.00005 also, but as you start to increase the step size, and it's not increasing by that much, the variance just goes up. It shoots up. In the case of vanishing gain algorithms, Again, this is not a very big run length. So for a small row, you see a big error because the algorithm still settling in. But as row increases, you see that the error starts to decay considerably. So it's much more stable as row decreases, right? And in terms of variances, it seems that the estimates are all good. I mean, it seems that between 0.5 and 0.8 are the best variances you get. And sorry, the dashed line here is just the optimal asymptotic covariance that you're supposed to get by applying PR averaging, right? This is all with PR averaging. I should have said that. So between 0.5 and 0.8, you get good estimates of the optimal asymptotic covariance, like something close to it. And but it's pretty homogeneous across different choices of row. It's pretty robust, I guess. When compared to constant gain, it's very sensitive. Right? And here, just four examples of sample paths with and without averaging. So 2 choices for constant gain, and you see that if the gain is too small, the evolution of the averaged parameter estimates takes a very long time to achieve theta star, and it will not converge, but the bias will be small because the step size is so small, but it takes a very long time to achieve it. And then the optimal choice of 0.0028 generates estimates are okay, right? But it's still biased. And then for the vanishing gain case, this is just a repetition of the plots you've seen previously. It indicates convergence to theta star as predicted by theory. Right? And PR averaging reduces volatility quite a bit and improves the convergence rate. And then here, again, same experiment, multiple independent runs. It's just histograms of the error between constant and vanishing step size algorithms. And here's really where you see the value of vanishing step size. Forgetting about 0.4 because the gain is too big for this short run to settle in. I mean, you get an okay estimate, but every choice here of row seems to generate histograms that are pretty robust, right? There's not a lot of variability in the histograms with averaging. That's what the red one is, right? You see the blue histograms have much more variability, but when you average across different choices for row, there's not much variability here. When you compare to the constant gain case, there's a lot of variability. So the optimal choice, 0.0028, gives you a good estimate, but everything else is just varies a lot, right? And for the very, very small gain that we saw that generated sample paths that looked fine, the histogram just doesn't even show up. Right? So, and these are all centered, right? They're centered in the optimal solution. So just to conclude, a few takeaways from this. For fixed step size algorithms, you have that the joint process is itself a Markov chain and it admits a unique invariant measure, but you also end up with an inherent estimation bias of order alpha of the step size if the noise is Markovian, multiplicative, and that the covariance in the central limit theorem for this recursion is not optimal. Now just a few topics. Open paths for research is to relax the crazy Lyapunov drift condition that you saw before and replace it by a simpler one, right? Which is just implies geometric ergodicity of the Markov chain, but without the need to have the crazy exponentials. And that might be possible with resetting. We need resetting because, again, as we saw previously in the MM1Q example, the second moment is not bounded, right, for the recursion. So in order to get that, we would need moment bound. So one way would to opt for the simple drift condition with resetting, right? Where what I mean by resetting is just what's commonly done in theory is that you select a ball across your space, state space of estimates. I mean, right? Not state space of a macro chain, but just you restrict theta n to a complex set. That's pretty much it. Every time it leaves the complex set, it lives at this complex set, you restart it inside the complex set. And another path of research is to find ways to eliminate the vector upsilon, right, or its average through design. And we have a success story of that. And that is true for stochastic approximation when phi is deterministic. Okay, and that's the theory of quasi-stochastic approximation. So through phi in this case, in quasi-stochastic approximation is typically a mixture of sinusoids, and by carefully selecting the frequencies of each of these sinusoids, we're able to conclude that the average of upsilon is zero for each theta, right? So it is error mean, and that would kill the major contributor of bias in this case, right? And then in this deterministic analog of stochastic approximation, we get much better convergence and estimation error balance for both vanishing and constant gain algorithms. Recall that convergence rate for vanishing step size algorithms in stochastic approximation was at best 1/n. And then here, recall that alpha is just 1/n to the rho, where rho is between 1/2 and 1. So this can be arbitrarily close. If rho is restricted to be strictly less than 1, this can be arbitrarily close to 1/n to the 4th. So it's much faster. And the same for estimation error bounds in constant gain algorithms. And but we don't have extensions to the stochastic case yet. And that's all I have for today. Thank you so much for your attention, and I'm happy to take any questions you might have.
All right, thank you, Caio. So we have time for questions. I can start. Can you talk about implications for TD?
Oh yeah, sorry, because I just saw a question in the chat. But yeah, go ahead. Implications to TD learning.
Mm-hmm.
Well, I mean, TD learning is a linear stochastic approximation recursion, right? And it has multiplicative noise. So I mean, I guess I don't know whether all the assumptions are met in TD learning. It depends on what Markov chain are you using, what disturbance are you using. But provided that the assumptions we have here are met, then these results hold for TD learning.
Well, I guess the question is, how would you apply TD learning? You know, what would your choice of step size be? And yeah.
In terms of a recommendation, maybe.
The recommendations.
Oh, yeah.
So,
Recommendation based upon these experiments is that you should favor vanishing step size algorithms instead of constant step size algorithms when possible, right? Of course, if your objective is varying with time, so suppose f bar was time varying, right? In which the objective now would be to track an evolving route rather than just a static route. Then vanishing gain algorithms don't make sense. But if your main goal is to solve, to is static route finding, then yeah, I guess the recommendation would be to favor vanishing step size algorithms.
Okay, so we had one question in the chat.
Okay.
So can your results for the linear stochastic approximation be generalized to nonlinear setting?
Yeah, we believe so, and we're looking into it right now, actually.
You gave one result, the target bias.
Oh yeah, right. But
So that's a pretty strong result.
right, yeah, that applies to linear too, of course. But yeah, that's the only result we have for in terms of asymptotic performance for nonlinear essay in this paper, and it's but we're looking into obtaining expressions for bias and asymptotic covariance for the nonlinear case right now. So that's an open path for research, but we think it's possible.
There's a question there.
Yeah, Pavel, just go ahead.
Yeah. I would like to know what happens if we relax the assumption of IID on the noise or the disturbances that are happening. So the setup that I'm thinking of is in a general process industry. When the machine starts up, there is a certain amount of noise which disappears when the normal operation begins. So if there are conditions where noise appears and reappears, how will we still look at vanishing step size as the best approach?
When does the noise disappear again? Sorry.
Okay, so what happens in process industry is that when the machines are cold and they're starting up, there'll be different kinds of measurement noises that are coming in. But when they are in their operating regions where they're built to be operating continuously for a long period of time, the noises changes. Like it's not going to be IID per se. It's going to be distributed based on other factors of the environment.
Mm-hmm.
So in that case, will vanishing step size be still a recommended approach, or will anything change?
Okay, so well, so can you tell me a little bit more about the noise? Do you know anything else? Like, is it
So
Markovian? Is it?
it's not IID, so
Mhm.
it's colored noise, and say standard algorithms that use colored noise in their theory development, like N4SID for identification of the systems, that fail in such a setup.
Oh, but I think there's a misunderstanding. So if the noise is ID, then constant step size might be fine.
Mm-hmm.
There's a lot of research to suggest that it's okay to use a constant step size.
Mm-hmm.
And it's in a case with a lot of memory, like you're talking about, that we think a vanishing step size is most appropriate.
Right.
I think that maybe the problem is that there is a transient period, and so it's a non-stationary setting, and then the worry is that the constant step size is going to get too small before the steady state is approached, and it's not a stationary system. I guess it's not even not stationary. It's like it's a changing system because
Yes.
during warm up, it's like works in a different way. I think that was the worry, but I think that the answer to that was before that the constant step size is not going to cut it if the system is itself is changing. So then, like, you probably have to tailor it to a specific application.
Mm-hmm.
By the way, can I ask a question?
Yes.
So for this recommendation of tapering off step sizes, I mean that's okay, but we only have one goal. Let's say, like you can't really, like in simulation, you can tune the heck out of it, but if you're on a real system, then you won't be able to do that. So do we also have something to say about like how to set these step sizes? Because again, like if you set it too small, then it's gonna be painfully, slowly converging. If you set it too large, then maybe you'll blow up the variance too much. So like, is there any hope that there is some universal way of setting the step sizes? And I'm very interested in this question.
Well, Caio, show your last slide again. Show your histograms. There.
Okay. All right.
So, okay, so before I talk about this, let me just say one thing, I guess, to Pavan, because he asked the question about the change of system. I guess from this, it would be more beneficial in general for you to choose a vanishing step size. Okay, but your problem seems. I mean, I would say it would be better to choose a vanishing step size in general, right? But if you're looking at a static root finding problem, now on the second question, but yeah, I mean, this histograms indicate that the most robust choice would be a vanishing step size choice, right?
Oh, wait, there are many ways of vanishing those step sizes. That's my question is like, what way?
Sure.
But look, they're all, at least in this, for this class of step sizes, one over end of the row, they're all the same. We're getting the same results as long as they're one.
Use in an asymptotic sense, right? So what if I care about finite time performance?
Maybe you can implement a mixture of constant and vanishing step size, so that you just.
The question is how to find it, though. I mean, that's.
Yeah, like just.
The Chaba wants to know what's the constant. So rho, it doesn't matter according to these plots, and we know the constant's going to be like a 1 over L sort of thing.
Yeah,
I guess but I'm also asking whether, like within the same class, you expect big variations depending on the actual choice of like the decay of the step sizes. Because I would expect that should be the case, but I don't know.
No, the theory says not at all.
Interesting.
Yeah, but it's incredibly insensitive to rho.
Right.
And the constant's going to kill transients for sure. A big constant that's too small is going to really hurt you.
Already for the IID case, if I just think about the least squares problem, if I don't know anything about the design matrix, condition number, minimum eigenvalue, whatnot, I don't know whether I can choose a very good step size for tuning for finite time performance. You see, this is what I mean. It's like an instance specific, like good choice versus a universal good choice, like how much do we need to give up, or do we need to give up anything?
Yeah.
Okay. Anyway, thanks.
Yeah, that's hard. Yeah, it sounds intractable. If you wanted to exactly optimize the best coefficient in rho for a given horizon of say 100 steps, it's I don't know the math for that.
Because in some special cases you can do this universally, but I don't know about the general case, so that's why I'm asking.
Yeah, well, with this memory, it's just nasty. Yeah. But I bet there's more that could be milked out of that disturbance decomposition, Chaba, because that martingale is close to your heart. And then that nuisance term with the upsilon is then something has to be treated with a different technique.
Okay. Interesting. I take a closer look later.
Yeah.